All right, so we're looking at chapter 3, number 18 and 19, and just graphs in general. These are truly challenges. If you can do this, you are ready probably for most things that are thrown at you in a first semester physics course. But graphs are a constant thing. And the general approach to any graph, it doesn't have to even be physics, is there are three main things that you look at. And the three main things that you will look at with any graph will be the values of any point on the graph, the slope of the graph, and the graphical area. Often just said area, but and so giving some color to this. They often people don't put little arrows, but physics people tend to. And so I'll make this kind of quick since you've got some of it on it and it could be good. So the value of, I'll call this A and this B, this is blue. So the points, any point on this graph tells you the value of A at whatever value of B. And so we really have to think about what is this, what does this graph mean? And when we do statistics and things like that, it's really easy for people to mess with things or analyze things. You have to look at the points. That's interesting. If this is position, then this will tell me position. And if this is time, it'll tell me the position at a time, whatever. If it's velocity, it'll tell me the velocity at a certain time, and acceleration will tell me acceleration. That's all we're going to do here in kinematics, but it's true for lots of things. The other thing that's going to be important are slopes. And so a slope, this is where the units, and we build on chapter 2 a lot. And when you get a new graph, and it's new thinking, it is slower. And you have to say, oh, the slope is the change in A. And then you look at the units of A divided by the change in B. And those are units of B. So then you say, well, what does that mean to have units of A divided by units of B? And so that slope, for instance, could be a positive slope, steep, a positive less steep, a negative steep. For example, if I connected those dots, we don't always connect the dots. They might be more smooth. It might be like this or something. And then the slope, we'd have to look at each point, and calculus is good for that. But still, the idea is the same, and the meaning is going to be the same. If I go straight, if it goes like that, I've got a positive slope, even though I got a negative value. And so, or I might do something like this: a positive slope with a zero slope, and then a positive slope, a less steep positive slope, and a negative slope. Well, what am I looking at when I look at that slope? Well, if it's position versus time, then it's meters per second. So I'm looking at a velocity because I'm looking at plus or minus. 0 on a position, that would be x versus time. So the slope there would be meters per second. That would mean that you're not moving. And you can see that that's kind of nice because a flat slope means you're keeping that same position. So the fact that x is not changing corresponds with the fact that the slope is 0 or the meters per second is 0. But that definitely takes some thinking, because there's a lot of different factors and you can see them different ways. But if I change this to velocity, it's a new, completely different meaning. Then I'm looking at the velocity at a time and the change in velocity over time. So that would be how much my meters, oops, wrong color. My meters per second change per second. So on a velocity versus time, that slope means meters per second acceleration, right? Right, acceleration. Position versus time, it'd be velocity. Velocity versus time, it'd be acceleration. Now, acceleration versus time makes this acceleration, and that's meters per second squared per second. There is a term, it's called jerk, and we generally don't get into it because it's just, there's other things to focus on and learn, and we, you know, it's not as, certainly not as an introduction. So on the acceleration versus time, the slope is, it tells you how much this acceleration is changing per time. And you often don't see that much. But the units will tell you, you know, what it means. You know, and occasionally with enough exercises, you'll scratch your head enough and figure that out. Now, the other thing that is of value is, people say area, but it's not spatial area, it's graphical area. So that's kind of a term that I've coined, graphical area. And you're going to get nice shapes. You can use this using calculus. There's all kinds of little clever ways, and computer programs do a good job too. But you're going to get nice shapes like a triangle. Well, I can calculate the area of that. How do I calculate it? Well, I take, it's half of that rectangle. So it'd be half of this, which is delta t in our case, or delta b to make it even broader. And then I would take the maximum value. So I go delta t times this, that times that, times a half, because it's a triangle. It's a rectangle. It was this whole thing, and I just multiply those two together. For calculus, that's called an integral. And I mentioned that in chapter 6. But
so please slow down and review that. So the maximum value is what?
So if I looked at,
Next line.
so for example, let's do this. Let's say we did this.
Because I think we had a question earlier about this where the triangle area ended up being half of what maybe
Yeah,
it
that's
should
right.
be.
That was the formula.
Right, but I want to make sure what the 2 units were
Yeah.
supposed to.
Yeah, so you see that the meaning is comes through in a nice simple example, which would be this graphical area. First, it's below the curve, so it'd be negative. And I would get it by multiplying the value of A times delta t. So one thing I could say is that for a rectangle, including a square, would be value of A times the change in B, which in this case is time. So if I took a smaller interval of time, or B, whatever that is, I'm going to get a small area. I'm still going to get the value of A times however much interval of time I have. the meaning will depend on what this axis is. And then just one more thing, and then we'll get into that. So a triangle, you can think of just like area. The triangle between this axis and that curve or graph, we call it. That's still delta B or delta T, really, we can think of it that way. Times A, but it's half of that rectangle. So the area would be 1/2. That maximum value of A, or however you want to say it. So it gets a little, words get a little max of A times that change in B. And that's for everything that we're doing, that's fine. Once you get the idea and the meaning, then you can, it really would be good to have that before you did calculus.
Mhm.
So, and yeah, you know, two things happen when you teach this stuff. One is you can assume people that it's clear, and you forget that it's clear to you because you've done it a bunch. And the other thing, that can happen is it's, unfortunately, you have to get through a lot of material and you've got to keep pace to
Mhm.
do the class. So, so thinking in terms of rectangles and triangles. Now, let's take a look. So this would be negative because it's below here. This would be, I would take, let's just do nice. So this would be a positive triangle. This I would calculate as
We
a,
can't really see because your screen's cutting it off.
oops, thanks. That would be a triangle. This would be a rectangle plus a triangle. And this would be another triangle.
Mhm.
But what does it mean? Well, first off, these would be positive because they're up here and they have positive values of A. So that's positive. And we generally always have positive change of B. So if it's down here, then you're going to have negative. But what does it mean? Well, it means whatever this says. So again, I look at the units. If it's position versus time, this one's interesting. Meters times seconds isn't a useful quantity.
Mhm.
So you can calculate it all day long. It's just not useful. No one cares.
To describe an area.
Yet the area of X versus T, that
Right. Doesn't make
matter.
any sense.
But X versus T here, meters per second, sure, velocity, or where you are at a particular time, what's your average velocity between two times, but this, whatever. And then I go back to, and you know, it's good to have a heads up because, you know, sometimes when that happens, we think we're the problem. If I go velocity versus time, then the point tells me the velocity at a particular time. The slope tells me the change in velocity per time. Acceleration could be positive or negative. Slope, negative slope. And the area would be velocity times time. And if we're using meters per second and second, what would that give me? Meters. And it would be a change in meters because it'd be not at a particular time, not where you are, but what you changed in that time. So it would be a displacement on a velocity. And that's in this graph. That's how you get displacement, is look at that graphical area. So for this, it would be the change in X is velocity times change in time. Meters per second times second gives me a displacement for that time. And you just, if you went from here to here, you just add it all up.
Can I ask you a question about this from one of the questions in the book?
Yeah.
So on 17A, 4,
Oh,
we take the graphical area of a And if you need a minute to look at it.
17A, part 4.
Part 4, yeah.
Find the graphical area for both Sage and the cheetah on a V versus T graphs. Include units and state what that gives. Yeah.
Right. So we did those calculations, and rather than ending up with the change, or what am I trying to say? So that was meters per second squared. And maybe it shouldn't. That's the first question. It was meters per second over seconds, or meters per
so-
second times seconds. So that would end up being meters. Isn't that
Yes.
right?
Yeah. It should have been a product for that, for
That was
this.
the first- that was the first thing. And then the other thing was that we were supposed to verify that's the same
Oh, yeah.
as the distance that was covered, or as the displacement. For those two, for the cheetah and Sage, but it ended up being half as much of the displacement. And so that I was curious if we've done the formula wrong, or if we got one of the units wrong.
What happens in the formula, so.
Or if I made a mistake.
Well, but I'm wondering, like, because with the rectangular one,
Hmm.
later we do a rectangular area, and that does end up being exactly the distance displaced
Mhm.
in the previous, term.
Mhm.
And so the question or graph, I should say. And then in this case, the triangular area, we ended up with half of the distance displaced, or of the displacement, I should say. Still getting the terminology straight, but we ended up with half of the displacement rather than the equal numbers to what the displacement was. So I'm wondering if we did it wrong.
Or if in my haste, I maybe,
But it seems like the triangle should show the displacement.
yes, yes.
So,
If it's velocity versus time, any area would be the displacement. So I can check that real quick too. Let me
because we
run.
did the calculation, so I mean, there's no giving it away. We can tell you.
Oh, I know. Yeah, no, you guys are in there. It's that's a great thing about this.
And then
You know, it's very, very much a learning thing, and so I don't need to worry about that. And I've keep fighting myself about giving exams, but I think it's kind of nice not to for you guys. But so let me finish one thing. Let's do a quick review, and let me do that one because I think I better check that. So if I go position versus time, that tells me where I am at a particular time. Change of position over change of time, that tells me my average velocity on the slope. Position times change in time tells me nothing, effectively. I go velocity versus time, that tells me velocity at a time. Change in velocity or change in time, that's average acceleration. Velocity times time is going to give my displacement. One more. It does start, you start getting used to it. And the beauty is you just look at those units and it'll keep you from jumping to a conclusion. This tells me the acceleration at a particular time. This tells me the change in acceleration per time, which is called jerk, which you don't use much. This is acceleration times time. And in that case, I can look at, meters per second squared times second. It's not going to be this, it's going to be change in velocity. And it could be a rectangle or a triangle. And in fact, if you divide by delta t, you've got A is delta V over delta t. So we really have to keep track of which graph we're doing. It's a great exercise. And then let's check out number 17. Is that okay so far?
Yeah, and I just want to say also, I don't know how much This is, oh yeah, I don't know how much time you have, but number 18 and 19, just to get the idea of what those are, something we definitely want to do.
Yeah,
And-
definitely. But I wanna, it's frustrating and when you have mistakes, and this isn't flawless because I was really pushing a publication deadline for 2 books.
Uh,
Yeah, if at some point maybe I'll tell you there were a couple answers that were a little wonky in the back, the earlier part, but not the most important.
What's that? Say that again? Oops.
What's it?
What? Yeah,
You're
I'm
stuck for a minute. Okay.
okay. Well,
Got you now.
okay. Chapter 3, number 17. Let's take a quick look at it. I'll do it fast, and you guys you've already done some of it. Okay, Sage is running with her pet cheetah. So I'm gonna have an S and a C. When you start your stopwatch, both are running at top
The weird answer for the area.
velocity. Okay, so both have a constant velocity. I'm gonna make a note. I'm gonna use some colors maybe. Cool. So I guess it could be green. So I'm gonna write symbolically, V of Sage is constant. And I'm gonna use, just writing this cheetah, V of the cheetah is constant. Just taking notes as I read this, so I don't mess it up. We'll set the origin to be where Sage is when you start the stopwatch. And her cheetah, subscript C, starts almost a football field away behind her position. Okay, so she's starting here. And the cheetah is starting here. And that'll be time 1. So I've got, where I want to keep track of this, time 1 equals 0.0 seconds. Position of Sage at 1 is 0.0 meters. And the position of the cheetah is negative. So the way I've done that, I'm going to call that plus. Don't mess it up. The position of the cheetah is negative 90.0 meters. Good. All right. Okay. After 3 seconds, Sage has run 15.0 meters, and the cheetah is where Sage started. Okay, so I'm going to do this. I think I'll draw that as a separate thing and just go, cheetah is now here. Sage has run 15 meters. Okay, so T2, I could do that blue since it's the same for both of them, but whatever. Is, and you take your time with this stuff, then it's a lot faster. So Sage X of Sage 2 is 15.0 meters. Now this is X of the cheetah 2 is 0.0 meters because I'm talking about position. After another 2.0 seconds, Sage has run another 10. Another 2.0, so that's 5.0 seconds. Position of Sage at 3 is 25.0 meters. And the cheetah kept going, thank goodness, past her. X of the cheetah at 3 kept going another 60.0 meters, 60. Okay, cool. Got that. really need more. So I see kind of what's going on here. Make a motion diagram. Okay, we did that. Then make a large position versus time graph and show both the line for Sage and that. How find the slope of each line using your result from part 2, make a velocity versus time graph and show both motions on the V versus T. You know, people definitely struggle with this, and then finally, okay, cool. So we're gonna do X versus T, V versus T from that, and then graphical area. I mean, this is a high level. This is people would be very thrilled to see.
Right. So I think the thing that we were concerned about was like on number 2 of this exercise. Did we calculate the slope correctly for both?
Yeah, let's do it. I'll do it kind of
The
quick.
area correct on 4.
I'm gonna do so we start our clock here, and the positions are all gonna be, well, no, we're gonna have a negative position, so that's good. Okay, so I'm gonna spread it out a little bit. Time, and that's in seconds. And I'm gonna just go ahead and go like this. We're gonna go from negative 90 to plus 60. I better give myself some room.
We did units of 5 meters. Seems to work pretty well for the question.
Cool. All right, so and this is part of moving the puzzle pieces. T seconds. Total 5 seconds. So that's going to be here. This would be 2.5. This would be 1, 2, 3, 4, 5, something like that. Okay, so, and you could write down 1.0 seconds, but it's pretty clear after that. Then we've got down here. We go from a position of 0 to 15, yeah. So 6, I'm gonna look at that and go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. Again, that's X in meters. Okay, 60. And I know that the cheetah, so I'm gonna go over here. Remembering that motion diagram and say that the cheetah is there. And then, so let's do this. This is going to be trouble. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90. Whew. Negative 90.0 meters. Need a bigger piece of paper. Okay, so at 0, Sage is at 0. Good. I can see the time and the position there. The cheetah is down here, which I expect. So the kind of that motion diagram will be kind of reflected in looking at the x-axis. Cheetah's back.
Can you plot the line from the cheetah's starting point to the ending point? Because I think I understand the new question about what.
Yeah. So then at 3 seconds, 1, 2, 3. Sage is at 15, and I like your 5, 10, 15. So that's where Sage is. Sage is right there, but when I run the time, I'll put Sage here. And at 3 seconds, the cheetah is now here, but that's at 3 seconds. So the cheetah is here. So that's the actual position. Cheetah, Sage, cheetah, Sage, cheetah, Sage. 5 seconds. Sage is at 25. 5, 10, 15, 20, 25.
Needed.
Cheetah is at here. 5 seconds, cheetah's at plus 60. Now I did this right. I got a straight line. We'll see. Which is probably not a very real thing. But if it's constant velocity, I should see a constant slope. And the slope tells me the velocity of the cheetah, and this slope tells me the slower velocity of Sage. In reality, you can't always just connect the dots with a straight line. All kinds of wacky stuff could happen. But in an introductory physics class, yeah, you know, and I already, by my telling you that it's constant, that means the slope is constant on this graph. X versus t. Find the slope of each line. Okay, so the slope of each line. So this would be, let's see, V of Sage, I'm going to do from 1 to 2. Change in X of Sage from 1 to 2 over change in T from 1 to 2. And I'll erase this in a second. So that she's gone 15 meters, 0.0, keeping the sig figs positive, in 3 seconds, 3.0 seconds, which is 5.0 meters per second in the positive direction. And you can see that she has moved in the positive. We good so far?
Yeah.
And then I want to double check this by looking, maybe I just want to make sure I didn't mess up. Let me go 2 to 3 and 2 to 3. 2 to 3. And so from 2 to 3, she went 10.0 meters from here to here. Or I can go from 2 to 3, an increase of 10. I could do 25 minus 15, whatever, in 2 seconds. Yay. And it's still the same. Good. I didn't mess that up.
We ended up doing 1 to 3.
Yeah, that's right.
Yeah. Yeah. And you could do it anyway.
Find either way.
Anyway. And so that's all cool. Unless it's specified, but, or unless it changes, which is, you know, often true when we run. Okay, cool. And then we do the cheetah in the similar way. So should I do that, or are you good with that?
Well, the cheetah is at issue because the area, it's looking like we're going to have to do an area of 2 triangles for the cheetah. And I think that's what we messed up.
Okay, let me check. Let me go 1 to 2 for the cheetah. And real quick, delta X of the cheetah 1 to 2. I mean, it's such a pain writing these subscripts, but it's so easy to mess up. So the cheetah goes positive 90 meters in those 3.0 seconds. And that becomes 30.0. I tried to do this so you didn't have to break out the calculator. So 1 to 2 is cool. Let's do V of cheetah 2 to 3. And goes, again, positive 60.0 meters in 2.0 seconds. And that's still 30.0 meters per second. So we should still be good.
Be no matter what. Be the 30.
What's that?
It should always be 30 for the cheetah also.
Yeah, and so from and I'm kind of checking my numbers too to make sure I don't have a typo or who knows. From 1 to, yeah, and if these two work, then 1 to 3 will also be, it'll be 90 and another 60. So that would be 150 in 5 seconds, which is still meters, seconds, still 30. So far, so good. That's consistent with saying that the velocities are constant. Now, let's remember that hers was, so let me put that information. I got the velocity of Sage is 5.0 meters per second. velocity of cheetah is 30.0 meters per second. Cool. The whole time. And
Mhm.
so, we good? Or
Yes.
question?
Yes.
Okay,
got it.
cool. Now I'm going to make a velocity graph. So it's not going to be too bad. You know, I mean, you can make this crazy, but then someone better pay you. So you go like this, you know, let me do a velocity graph. This is going to be easier for me. It's all positive, so I can even just drop that guy way down here, whatever, it's going to be positive. I'm going to kind of line it up here. T seconds, velocity, meters per second. And when the mistake we make is when it's in our short-term memory, we think, why do I have to write that? But then when it leaves our short-term memory, we're happy we did. Or someone else looks at it. So 5, 3, 2, something like that. And you can do it nicely too, but in this case, I've got 5 and 30. So I'm going to go 5, 10, 15, 20, 25, 30. Whew. And that's just maybe just experience, or I don't know what, just being able to see that. But this is V meters per second. This is 30.0 meters per second. I've got it there, so I can 5.0 meters per second down there. Okay. And so her graph, she's always the entire time her velocity the entire time is flat. It's constant. A constant velocity here is a constant slope. A constant velocity here is a flat line.
Oh.
And then over here, yeah. And so, you know, it's just easy to jump to conclusions. And the cheetah too is a flat line. And so in both cases, you've got rectangles.
I see why it was half.
And then we used the wrong, and then we did the wrong calculation.
That
formula.
explains why the area was half.
Yeah. Yeah. But you know, that, see, and that's really great work that you guys did. And now you're just like, oh, a tiny correction and polish and you're good.
So my graph looks bad now.
Yeah.
Time making your graph look neat. So
Yeah.
So cool.
okay, that answers that.
Yeah, I'm gonna stop this video, so it's a separate video, and then we'll look at 18, 19.
All right.
Yep.
Stop recording.